reduce parameters when we need, but always we will come back to the world of the physical parameters, because this is the only one existing. The reduced parameters are only a solution to solve the problem, a solution to make the problem easier. But this is not an existing world. This is not a real world. So you will always need to go back to the world of the physical parameters. And this is a very nice example. So in the world of General Electric, they work with this, but at a certain moment they will always indicate the limit or the margin compared to the limit by using N1, recalculating N1 from the value you have there. I will explain you three, let's say, situations, three situations where this rationale based on the trust setting parameter and the parameters that we have explained there, the trust, the reduced trust, the TIT, the reduced TIT, etc., can be useful. In order to show you why are the manufacturers using these trust setting parameters. The first example, this is something that I have explained to you already in the past. This is the problem of the flat rating. I have indicated you that it was a problem related with the shaft horsepower, because I explained to you that in the turbo shaft. Of course, in the world of the aircraft engines, we do not speak in shaft horsepower, except for the turboprop, of course. What we have said for the turbo shaft, you can extend it to the turboprop. But for the turbofan, it's not the case. And what's happening? So you have your turbo shaft with a shaft here, with a turbine. So we have here a compressor. Here we have a turbine. So, and here we have a casing. We have combustion chambers, etc., etc. So what's happening? You remember we indicated that related with the atmospheric temperature that we call also the OAT. And in fact, the thrust is increasing for a reduction of the OAT with an influence of the TIT. This is a curve like this. When the OAT is lower and lower, I have more and more thrust. Or when the OAT is increasing, I have less and less thrust. And this is with the TIT increasing in this direction. But what's happening when the thrust is increasing? When the thrust is increasing, everything in the engine is increasing. So the pressure ratio here is increasing, the TIT here is increasing, the mass flow rate here is increasing, the fuel flow is increasing, everything is increasing, okay? So there is a global increase of all parameters. What can be the consequence of that? The first consequence you could have, this is that the power that you have here on the shaft, that is corresponding to a certain rotational speed multiplied by a torque, is increasing. That could lead to a too large increase of the torque. You could break the shaft. But there is also something else that is happening. Here you have, and that was not the case in the turbo shaft, here you have the pressure PA. You have the pressure, let's say the PT2, let's speak about the maximum pressure here. The PT2, when you increase the, let's say, power available in the system, the PT2 will have a trend to increase. Everywhere you have more energy here that is pushing on this very big nacelle we have. And in the outside world, we have PA that is acting against this nacelle. What could you have? You could have this nacelle that could explode. Nacelle or the carter. So the envelope of the engine could explode due to a too large pressure difference between the inside world and the outside world. And so you would have an explosion. And we can see that, I will distribute that in the slides, that in fact this limit, let's say the limit due to P in compared to P out, P in that is becoming too high than P out, we can see that this limit in fact is changing with P out. When the altitude is decreasing, PA is also decreasing, and for a same pressure here, you will explode more easily the carter. And so what will you do when the internal pressure is when the external pressure is decreasing due to higher altitude, you will also decrease P in, and in fact the limit thrust is proportional with the altitude. When you increase the altitude, you will decrease the limit thrust. So if you want to indicate the F limit, there will be a limit thrust that could break the shaft, but that could also explode the external carter of the engine. If you take this in function of the altitude, and the altitude is decreasing, the limit thrust will be a function like this one. Maybe it's something that you will expose like this, by a step function, something like this, but there will be a relation between the limit thrust and the altitude. And so, like in the helicopters, in fact, you will fix a F limit, so a maximum limit, and of course, you will fix a TIT limit, so a thermal limit here, and a mechanical limit here, a mechanical limit here, due to the risk that you could have on the shaft and on the external carter. Also, of course, as we have seen in the helicopters, maybe you could have some emergency situations, some emergency ratings where you would have a certain time at which it would be allowed to go a bit higher. That can be, for example, what you have in what is called ETOPS conditions. I will not go much further on that. But, as I said, this F limit is depending on the altitude. So if you put the altitude here, so you see that this limit that you have here will decrease in this direction. And in fact, you have exactly the same phenomenon. So when you decrease the altitude, you have also the thrust that is increasing with the altitude. And you will have a certain limit that will not be parallel with the shaft, but a limit that will go down like this. This is the F limit that you will have on your system. So it's a very complex situation because it's a 3D problem where you have these two parameters that are in fact changing independently of each other, because you can be at a certain altitude with an OAT that is x, x plus 2, x plus 4, x plus 6, x minus 3, x minus 4, depending on the season, if you are day, night, etc., etc. But if we look at the problem, we need to understand how this problem can be solved. Because you are the pilot controlling the engine, or you are the engineer developing the FADEC, the Full Authority Digital Engine Controller, the control system of the engine, and the FADEC is not deciding by himself what to do. You need to introduce some guidelines, some limits, some constraints. And when you look at this, you see very clearly that there are two constraints. There is one here. This is maximum TIT. And arriving in this point, you have a second constraint, which is F limit. You see very clearly, if you are at a certain altitude, I forget the altitude, you are here, you are following the maximum temperature limit, and at this point, you cannot continue in this direction. You need to change the direction, and you need to change the limit, and you need to follow this F limit. You see that you change your attitude as a pilot, or you change your regulation law as an engineer introducing the control law of the engine at this temperature. We call this phenomenon the flat rating. So we call this temperature the flat rating temperature. Of course, this flat rating temperature is a function of H, because you see that F limit is reduced with the altitude. So that means if you have a lower F limit, let's say here, you see that the flat rating temperature will be there. So you see that if you have a higher altitude, you will have an impact on the flat rating temperature. And of course, this must be analyzed in some details. It's not so easy to see exactly. It will change by 0.1 degree, by 1 degree, by 1,000 feet. So it must be, of course, analyzed with a lot of details related to the structure of the system. But we have clearly a change of the flat rating temperature with the altitude. Okay, but why are we speaking about that? Why are we speaking about that? This is because the engine must know, through the pilot or through the regulation system, where he is. Let's say the engine is here. Sorry. The engine is operating at this OAT. This is the OAT of the summer, because you see it's a high temperature. What is the limit then that you give to the engine? This is this limit. Okay? And if we are today in the winter, that we have a much lower temperature, what is the limit that you give to the engine? You give it this limit. Easy. Very easy. I give this value and you give this value. Okay. Except that nobody is measuring the TIT and that nobody is measuring the thrust. So how will you, as a pilot or as a control system, indicate to the engine that he needs to stop